All right. Okie dokies. So, thank you both for coming. Maybe we'll have some more people trickling in later. Again, the way this works is just go ahead and put any sort of questions you have in the chat box. We also had, I had a student email me earlier this week and asked me to go over some questions. So basically, we're just going to be doing some practice problems and trying to stay on top of this material. So to start off with, do you have any questions about what's going on last week and this week in chapter 1? I'm gonna take that as a no. So we're gonna just go ahead and start with chapter 1, section 1, if that's all right with you two. And we have a couple questions that have been requested from this section. And then we'll just go through 1.2, 1.3, 1.4, 1.5. Okay. So we're going to start with 1.1, and this is talking about like what is a function, and we're going to be on page 6. I basically go through, I use the book, and I find these problems, so it's probably very convenient to have the book with you, because I don't always write out everything that's in the problem, but I will make sure that I read it out loud. So we're on page 6 right now, and we're going to do questions 17 and 19. So for question 17, or for these problems, we have the function s is equal to f of t. So I'm going to write down that up here. S is equal to f of t. And s is, oh, give me just one sec. Okay, so I just had a question in the chat box that says that is asking about these sessions being available as recordings, and yes, they are being recorded, and I will post them right after we're done here. So you don't always have to be here live. But if you do want to ask questions, either email me beforehand so that the questions can be answered and you can watch the recording, or be here live, because otherwise I won't know you have questions. Okay. So this is also S is equal to the annual sea level in meters. And T is years before 2008. All right. So we're trying to come up with different expressions to describe different scenarios. And this is going to be useful as we go on, just as like interpreting like word problems and stuff like that. So for 17, we're trying to find an expression that will tell us about the average annual sea level in 2008. Does anyone have any ideas about what this is going to be? All right, 0. Yes, that's like a good place to start, because we've recognized that T is equal to 0 because the year equals 2008. So rather than it being equal to 0, what we're going to do is S is equal to F of 0, where this is the beginning. This is what it is in 2008. Does that make sense? Awesome. Okay. What about for number 19 then? Now we're trying to find the average annual sea level. We're trying to find an expression that represents the average annual sea level in Aberdeen increased by 1 millimeter from 2007 to 2008. Where should we start with this? Any ideas? Yep. So we're going to start with, actually, it's going to be F is, sorry, my handwriting is going to be F of 1, not F of -1, because of the way that this is written initially up here. We're saying that T is years before 2008. So 2007 is T equals 1. But yeah, we're going back 1 year, so we're looking at F of 1. And so that is going to be the sea level in 2007. Okay. What else do we know to create this expression? Because we're not just trying to say what is the sea level in 2007, we're also trying to communicate that between 2007 and 2008, there was a difference of 1 millimeter. So 1 millimeter is going to be 0.001 meters. From 2007 to 2008. And we know that this is F of 1 and this is F of 0. So what we're going to say is that F of 0 is equal to F of 1 plus 0.001. Yes, exactly. You have it in the chat box right there. Perfect. So in the chat box, it was written as minus F of 1 is equal to, but these are the same thing, and they're both communicating the same thing. And that is that the difference between 2007 and 2008 is 1 millimeter. Perfect. Awesome. All right, I'm going to clear this in just a second. Are there any questions about this? Yes, both of those would be considered a correct answer. They're equivalent. So you could put whatever you want, as long as, you know, it's equal to this. Okay. Then we also had questions about 25. I believe this was on your homework for last week. And that's where these questions are coming from. So we're still in 1.1. Now we're on page 7. 25. And we have A, B, and C, different parts. Okay, so we're given a graph to interpret. And as you'll see as this semester goes on, my graph drawing skills within Zoom are not exactly the best. So it's always nice to have your book handy so that you can see like what the graph is actually supposed to look like, because like I said, not exactly the best, but I do my best. So what are your thoughts about the original deposit? So A, it's okay. Yes, exactly. It's 1,000. And the reason that is because here, when t equals 0, the y-intercept is at 1,000. So awesome. So it's $1,000. Right. This is in money. Yep. Okay. Now estimate f of 10 and interpret it. So f of 10, so we're going to say that t is equal to 10. That's going to be like right here-ish. And it's going to be like right here. So we're saying that t is equal to 10. So that's 10 years. And we're trying to find the balance at 10 years. And so that is going to be equal to $2,000, approximately. Right? Yeah. It's a little higher than 2,000, but so t is equal to 10. We're finding the balance at 10 years, and that's approximately equal to $2,000. All right, and then what about C? Now we're saying, when does the balance reach $5,000? How are we going to approach this problem? Thoughts? Okay, so okay. Yeah, I would say closer to 21, but what you're going to start with doing is finding where $5,000 is. You're going to go across on the graph, and you're going to put a mark there, or at least this is how I approach the problem. And then you're going to try to figure out exactly what the time is. And so I said t was approximately equal to 21. So it'll be f of 21 is approximately equal to $5,000. And so to answer the question, when does the balance reach $5,000? It's going to be in about 21 years, because this is in years. All right. And we have one more from section 1.1 that has been requested to do. So if there are no questions about this, we'll start on that one. Any questions? Okay, so the number of sales per month, S, is a function of the amount A in dollars spent on advertising that month. So S is equal to F of A. Then part A is interpret the statement F of 1,000 is equal to 3,500. Thoughts, comments? What does this mean? This is something that's going to happen a lot. Yes, exactly, in the chat. $1,000 in advertising is equal to $3,500 in sales. This is something that's going to happen a lot in this class. Is you're going to be given an equation and asked to figure out like what it means in the real world, because a lot of what calculus is once we get into the calculus of this, it's describing what's happening in the real world. So that's why I like calculus. I'm a total nerd though. Anyway, it's important that you be able to interpret equations like this. So $1,000 in advertising spent, and you get sales, get 3,500. Okay. All right, so then part B, which of the graphs below is more likely to represent this function? Well, when I started this problem, I asked myself, what is more logical to happen? Is more advertising going to cause, here, let's do it like this. Which of these is more likely? More advertising is probably not going to cause less sales. It's going to cause more sales. So we're going to be looking at something where as the advertising money goes up, then sales go up. And the way that we graphically are going to represent that is going to be as something with a positive slope. So I spend more on advertising, I get more in sales. Does that make sense? So I decided it was going to be a positive slope. That leaves me with graph number 1. Does that make sense? Are we all on the same page there? Awesome. Okay. And part C, what does the vertical intercept of the graph represent in terms of sales and advertising? So what does this point mean? Well, the way I approached it was I said that point is when A is equal to 0. So that's when there's no money being spent on advertisements. So that's basically sales without ads. So if there's no ads, how much do we sell as like a baseline? Okay, any questions about this problem? All right, let's move on to section 1.2 then. Okay, does anyone have any particular questions about 1.2? Yes, no, maybe so. Okay, let's do some stuff with these lines. So we are on page 12. And let's just do a few problems from 1.2. Let's do number 6. And let's do number 10 to start with. Okay, so for number 6, we have an equation, and we're just trying to figure out what the slope and the y-intercept is. So our equation looks like this. First thing I'm going to do is try to put this in a form that I can understand better. So for me, that's going to mean putting it in the form y equals mx plus b, because then I have my slope and my y-intercept given right there. You guys talked about this earlier in this section, I think. Yeah. So I am going to subtract 3x from both sides. I have 2y is equal to 8 minus 3x. I'm going to divide everything by 2. So I have y is equal to negative 3 over 2x plus 4. So now that I have it in this form, my slope is going to be m. And my y-intercept is going to be b. Everybody cool with how that happened? What a slope and y-intercept is? It is actually, because this is one term. So what I did was I said that this is going to be 3x divided by 2. And what I did is I just pulled the x out of here. So I said that 3x divided by 2 is the same as 3 over 2 times x. Because this is actually x over 1. And so if I were to multiply 3 over 2 times x over 1, I would end up with 3x over 2. Yeah, no problem. Just keep asking questions like that, just to make sure we're on the right page. So that is why I pulled the x out. And I do that just because it's easier for me to see the slope then. So yeah. Okay, awesome. Let's do number 10. So number 10, we're going to need the book again, just to look at this graph, because I'm not going to be able to draw this successfully. So number 10, part A, is asking which of these lines have the same slope. Can you guys pick out 2 lines that have the same slope? And then we're going to also do part B, if you guys want to think about that too, and which of these lines have the same y-intercept. So for the same slope, that's L2 and L3, and that's correct. These lines are parallel to one another, so they're not going to ever intersect because they're both increasing at the same rate, essentially. And for part B, we have a vote for L1 and L3, again, which is correct. So L1 looks something like this. Nope, that goes through 0. And L3 looks something like this. And so they both have positive slopes, and they're hitting the y-axis at the same time. Okay, so for part A, which of these two lines has the larger y-intercept? L2 or L3? It's going to be L2. That's this one on top. Because it is further up the y-axis. So L2, larger y-intercept. And then down here for part B, which of these lines has the larger slope? We just talked about this too. We have L1 and L3, and L1 is going to have the larger slope. Okay. Do you have any more questions about 1.2 and working with linear functions like this? Number 14, yeah, for sure. Okay. Let's do 14. So which of the following tables could represent linear functions? So to do this, we have to determine like what a linear function looks like in comparison to other functions. So a linear function has a steadily increasing slope, right? So as x increases by the same amount, y is going to increase by the same amount. That's like rise over run. So for A, we have x equals 0 to x equals 1. So the slope from that is going to be, not that. It's going to be rise. So that's going to be 25 minus 27 over run, which is going to be 1 minus 0. Or at least this is, I'm basically, what I'm doing here is I'm finding the slope between these 2 points, right? I'm saying, yeah, finding the slope between these 2 points. So that is going to equal -2 over 1, or -2. And a characteristic of a linear function, consistent slope. So the slope of the line is always going to be the same, regardless of what 2 x values you choose. So what I'm going to do is I'm going to compare the slope to a different set. So I'm going to say 21 minus 23 over 3 minus 2 is equal to -2 over 1. And so this is also equal to -2. And if I were to look at the other ones, I would have 23 minus 25 over 2 minus 1. So this is going to be a line. And why is that? Because it has a constant slope. And just for practice, can you look at this table and tell me what my y-intercept is going to be? (27). Exactly, because that's where x equals 0. Awesome. So let's try B. So we're going to do this exact same thing. We're going to say T is going to be basically our X, and S is going to be our Y. So we have 72 minus 62 over 20 minus 15. So I'm going to find the slope, and this is going to be 10 over 5. 52, 62, 20 minus 15. Okay, so this is going to be 2. And so there's my slope for the first one, and then 82 minus 72 over 25 minus 20. This is also going to be 10 over 2, or 10 over 5, excuse me, which is equal to 2. And then I have 92 minus 82. And so this follows the same pattern for the rest of the thing. So we're also going to say this is a line. And we could figure out what the y-intercept is going to be, but we don't really need to for this problem. So yeah, there we go. So this part B is also going to be a line. And finally, let's look at part C. So here we have 10 minus 5 over 2 minus 1. And so this is going to be 5 over 1, so that's going to be 5. And then we're going to do, always put the rise on top. 18 over 10 minus 3, or over 3 minus 2. So this is going to be 8 over 1, and so that's going to equal 8. C is not a line, exactly, because these two slopes are not the same. So the slope is getting larger over time. So the slope here, we could say, is 5, but the slope here is 8, so we've got a curve going on. And so this is not a line. All right. No problem. Let's move on to section 1.3. Okay, so now we're going to be talking about average rate of change, which is essentially slope in this case, like when we're discussing like a line. And it's very important that conceptually you guys are very comfortable with average rate of change, because when we get into like the calculus of this, it's going to be about like instantaneous rate of change. So we're like going to be using average rate of change a lot to just kind of understand what's going on in terms of the calculus. All right, so 1.3. Let's start with problem 8. So we're finding the average rate of change of the equation f of x equals 2x squared between x equals 1 and x equals 3. So what I'm going to do is I'm going to say, all right, I got to find out what f of 1 is equal to and what f of 3 is equal to. So f of 1 is going to be 2 times 1 squared, which is 1. F of 3 is going to be 2 times 3 squared, which is going to be 9. So this is equal to 2, and this is equal to 18. And then I'm going to do my equation, f of 3 minus f of 1 over 3 minus 1 to find my average rate of change, or to find the slope between these 2 points. So that's going to be 18 minus 2 over 2, 16 over 2, 8. So average rate of change. And I'm going to use ROC to designate rate of change a lot, especially in the first part of this class. So average rate of change. This is also the slope. Cool. So if I were to draw a line between Those 2 points. Okay, so basically what this is saying is just kind of to give you a little bit of a roadmap to where we're going. This graph looks, I don't know, something like this. It is a curve. It's an exponential curve. That looks atrocious. See what I mean about not being great at graphs? In Zoom. Okay, so let's say our graph kind of looks like this. I'm going to make that into an arrow so it's a little foolish. And we have this is 1, and this is 3. I'm going to draw a line between these points. And so this is the slope of this line is going to be, that is not necessarily what's going on in the actual graph. But we're using this to approximate what the average rate of change is going to be. So the whole point of calculus is that eventually we're going to be able to figure out the instantaneous rate of change at any point along this black line here, and not this green line that's representing the average. So that's kind of where we're going to be going, and that's the meaning of this whole problem. Yeah, so the average rate of change basically means it's the slope between one point and another point. So if I were to have a graph that looked like this, so actually that's too consistent. Let's make this messy graph. Doesn't look very pretty. And I want to find out the average rate of change from here to here. So x equals 5 and x equals 20, right? So I could like figure out what the rate of change is all along this line here and try to figure out what that is, or I could just find out what the average rate of change is. And so the average rate of change is just going to be what is f of 5, what is f of 20, and I'm going to ignore all of this nonsense in the middle, and I'm just going to go straight from 5 to f of 5 to f of 20. And this is the average rate of change. But it's only between these 2 points. Yeah, it's not every point on this graph. So when I'm looking at average rate of change, it's just I have 2 points, and it's the slope between them, and there's nothing else going on. I'm ignoring all of the other nonsense that's going on. All I want is f of 5, f of 20, 5, and 20. And that's all I need to find average rate of change. So this is useful in some situations, but for instance, in the situation of this graph that I just doodled, there's a lot of stuff going on in here that you just wouldn't get if we only looked at the average rate of change. And so that's the point of calculus. But for now, like, this is basically a very dramatic example of what the average rate of change can look like. Cool. Okay. Let's do number 16. And yeah, let's do number 16. So at time t in seconds, a particle's distance s of t in centimeters from point given on the table, what is the average velocity of the particle from t equals 3 to t equals 10? Okay, so this requires some knowledge of vocabulary. Velocity is basically the rate of change of distance. And so like, this is something they like using velocity a lot. So in order to find a velocity, we have to find what the distance is, and then it's like what the rate of change is. So fortunately, we're given a function for distance. We're given s of t, which is distance. And we're asked to find the average velocity, or the average rate of change. So we have all of the information we need to solve this problem. So we're trying to find the average velocity of the particle from t equals 3 to t equals 10. That means that we're going to have a function that looks like this. Not f, because we're doing s. It's going to be s of 10 minus s of 3 over 10 minus 3. And so this is going to be 144 minus 72 over 7. And so it'll be, what, 72 over 7? And I don't have a calculator on me, so I can't really simplify this, but you can divide that out and you'll get some number. And so this is 72 divided by 7 centimeters per second. The reason I tend to leave these in fraction form is because you're not allowed to use calculators on your exams, and because you can't, then this is the form that the answer will be on the exam. But if in your homework, you can just stick that in a calculator, 72 divided by 7. So yeah. Am I going to at all be concerned with what S of 6 is? The answer is no. Yes, exactly. Because it's not what I'm considering. I'm only looking at the average rate of change between 3 and 10. I don't really care what happens in between. Thus the average. Okie dokies. How are you feeling about section 1.3? Thoughts, comments, concerns? Awesome. Okay, let's move on to 1.4 then. And this is cost and revenue. Okay. So basically, this is the business part of this calculus for business. We're going to be using some applications in terms of business. So let's look at 1.4. And we are on page 35. All right. Let's do questions 2 and question 4. All right. So approximately what quantity does this company, given the graph below for question 2, approximately what quantity does this company have to make in order to make a profit? So we want them to make a profit. So we want the profit function, profit, to, oh, this is something else I tend to do. If you're going to be regular at GSGs, whoever's with me or watching, I'd have a tendency to separate things into what I want and what I have in terms of organizing information. So I want a positive profit function. What that means is that I need my revenue to be greater than my cost, correct? Because profit is equal to revenue minus cost. And if revenue is greater than cost, then my profit will be positive. So I want a positive profit. I want my revenue to be larger than my cost. I have this graph that's showing me what the difference between revenue and cost is. So basically, what I want is, where do these intersect? And that's going to tell me where revenue is equal to cost. And so any revenue or any Q, any quantity produced larger then the point where revenue is equal to cost, we'll be generating a profit. So I'm going to look at this graph, and I think that's like maybe 325. Let's call that 325. So this occurs at Q is equal to 325. Approximately what quantity does this company have to make in order to produce a profit? Well, this company has to make more than 325 of its product. Does that make sense? Awesome. Okay. Oh, there's two parts to this number 2. So then we're going to be asking estimate the profit generated by 600 units. What we'll do there is we'll figure out what R of 600 is and what C of 600 is. And this will equal the profit for 600 units. So R of 600 looks to be about, let's call that 2,500. It's a little less than that, but we're just doing some estimates right now. And then we have the cost at about 600, which is going to be I don't know, something like that. And so then we'll just subtract these. So that's what, 250, 750. So my profit is going to be approximately this. So looking at this graph, if I make like 2,000 units or 2,000 like products, do you think my profit will be larger or smaller than if I make 700?
Mathematics.
Somebody, yes, it's going to be larger. I think somebody has a mic on. Does somebody have a mic on? Okay. So yeah, so if I make like 2,000, it's going to be a larger profit than if I make like 700. Awesome. Okay. Do we have any questions really more regarding 1.4? Do we want to do more problems here? Do we want to move on to 1.5? 1.5 tends to be a problem for people. So I did want to like focus on that today, especially because next week we're getting into logarithms and more exponential functions. So I just wanted to make sure everyone had a really good foundation with 1.5. So if nobody has any objections, that's where we're going next. Oh wait, we still need to do question 4 in 1.4. Oh. All right, let's do question 4, then we'll move on to 1.5. Okay. So values of a linear cost function are in the table below. What are the fixed costs and the marginal cost? So find a formula for the cost function. So what are the fixed costs? Let's think about fixed costs in terms of like, what does a fixed cost mean in terms of a linear function? What am I looking for? Starting point, exactly. So the fixed costs, yeah, they're going to be the same throughout. I like thinking of this in terms of like a line. So let's say I have this line and it looks like this. The equation of this line is going to be y is equal to mx plus b. My fixed costs is this B here. So when I am not making anything, this is the cost of not making anything, essentially, because this is like the baseline cost. So in order to find that out, this is going to be our Q axis, and this is going to be our C. This is the function C of Q, and this is, we'll just call this Y. So this is going to be Q and not X. Q. So we're looking for Q is equal to 0. So our fixed costs for this are going to be $5,000. Okay. So if our fixed costs are $5,000, what is our marginal cost going to be? So our marginal cost, in terms of this equation that I have down here, is going to be this M, this slope. If I move from making 0 to 1, so I'll say that's Q equals 1, like what is that change going to be? And so that change is going to be, we can do this by 520 minus 5,000 over 5 minus 0. So this is going to be 20 over 5, which is going to be 4. So our marginal cost is going to be equal to 4. So this point here is going to be 1, and then it's going to be 5,000 plus 4. So this is 5,004. So I move from making 0 to making 1, and it costs me $4 more to make one product. Thoughts, comments, concerns? Taking that as a no. All right. Let's move on to 1.5 if there are no more questions. Okie dokies. Okay. So we're going to start with this question 2. All right. We're looking at, so we're given these functions. So we're looking at the initial amount where t equals 0, and we're looking at whether the function represents growth or decay, and we're looking to find the growth or decay rate. So we have 3 things that we need to find for each of these different functions. Here we have a. So we're going to use the same methodology for all of these. But the answers are going to be different because they're just different functions. So feel free to put in the chat box if you have any ideas regarding number 1. This first one here? Okay, yep. So our starting is going to be 100. And the reason that is because t is equal to 0, right? And so if I have any number, I'm going to use this x to say any number. So any number to the 0, that is going to equal 1. So I could pick whatever number I want to be here, and it's always going to equal 1. So this is going to be 1 times 100 to get our initial value. So that's just kind of like a rule of exponents that makes this process easier. Okay, so is this growth or decay? Growth. Exactly. Because this is greater than 1. And finally, what is my growth rate? %, exactly. Because what I'm looking at is in here, this is going to be increasing by 0.07 or 7%. Awesome. Okay, so we're going to use that same methodology for this part. So we're going to find out what our initial is. Our initial is going to be when t is equal to 0. So this is equal to 1, this chunk here. 5.3, exactly. Is this growth or decay? Growth. And what is my growth rate? Going to be 5.4%. Yep. Cool. Let's do the same thing here. Our initial is going to be right there, so that's going to be 3,500. Growth or decay? Decay. And that's because this is less than 1. And what is my decay rate? 7%. Awesome. And finally, here we have the initial value is going to be equal to 12. This, as we established before, because this is less than 1, this is going to be decay. And my decay rate is equal to, what, 12%? Cool. Everybody okay with interpreting equations like this? So everybody can look at an equation. Yeah, okay. But what we're going to encounter next week is that there are different ways of writing these equations. And so that's something that we're going to focus on the GSG next week. But if they're in this form, you guys are totally able to interpret what the growth rate is, all of that jazz. So this is something that you can interpret, and that's the goal of this week, is to make sure that you can look at an equation that looks like that and tell me like all sorts of jazz about it. Okay. So let's do question. Let's do, growth versus decay. Yes, for sure. So, question in the chat box asking to explain growth versus decay. Okay. So, like graphically, they're going to look a little bit different because a growth is going to be increasing like this. So I start off with small increases. Like, for instance, if I were to do this in terms of average rate of change, my average rate of change here would be a tiny slope, but my average rate of change here would be a larger slope, and my average rate of change here would be an even larger one. And theoretically, I'm moving the same x distance each time. So basically my slope just keeps increasing. And that's kind of like the idea behind this whole exponential thing, is that it just keeps getting bigger and bigger and bigger, and it keeps increasing faster and faster and faster. In terms of decay, it's basically the same thing, but going in the opposite direction. So here we have fast drops, like it's getting very small very quickly, and then it gets slower and it gets slower, and finally this is slow change. So if you think about it in terms of changes, we start with a small change in growth, and it gets to be a big change. And then we start with a big change in decay that gets to be a small change. So it'll be from here to here. So this slope is larger, more negative. This is something that we're going to be using a lot, like comparing, is this slope more negative than this one? So I'm going to say the absolute value of the slope is larger. It's more negative than this chunk here. And then this chunk here. So it's like flattening out, sort of thing. Does that kind of explain like the difference between growth and decay? Another way of thinking about it is that for growth, as x increases, y gets very large. And for decay, as x increases, y gets very close to 0. Oh, okay. Yes, okay. So say I have a function a is equal to, we'll do, this is C from the last question. So this was our question. This is going to be, if you think about it in terms of, okay, think about it like this. So a is equal to 3,500 times 1 to the t. 1 to the anything is going to equal 1, right? So this is always going to be 1, and a always equals 3,500. Up here, I have 0.93 to the t. This is less than 1. So if I have t equals 2, for instance, it's going to be 0.93 times 0.93, which is going to be less than 0.93. And this is going to keep getting smaller and smaller and smaller. So as t gets larger, 0.93 to the t gets very small. So then I get to ask myself, how does that affect the rest of this equation? So if that's the case, then this is going to be a is equal to 3,500. And as t, I'll just rewrite this. So as t gets large, this is going to be 3,500 times very small number. So this is going to be a gets smaller. So we start off at 3,500 and a is going to decrease. Do you see how I kind of started from what happens to t to what happens to a? So it's kind of just about like relating, like if what happens if t gets very large? Like theoretically, if I have a large t, what's going to be happening to the function? Am I making sense? Am I answering your question right? Awesome. Okay. So basically it's the same thing if you do it the other direction. For instance, if we had A is equal to 3,500, and this is going to be 1.09 to the T. So 1.09 squared is going to be larger than 1.09 because it's just getting larger. So as T increases, or T gets larger, then what's going to happen to this chunk? Well, this chunk is going to get very large. And so A is going to get very large. So I'm going to clear this information, and we're just going to kind of sketch this out really fast. So this is A is equal to 3,500. And so this is if it's A equals 3,500 times 1 to the T. And then my decay starts here and gets down. So this is if A is equal to 3,500 times 0.93 to the T. Because I'm starting here at 3,500, and then it's getting very small. So A is getting continuously smaller, and here it's getting larger. So this is my theoretical. Okay, awesome. Okay, like I said, exponential functions are going to be very important as we go on. So I just want to make sure everyone's on the same page. Okay. Let's do number 6. So the gross domestic product, G, of Switzerland was $310 billion in 2007. Give a formula for G in billions of dollars T years after 2007 if G increases by 3% per year or G increases by $8 billion per year. Okay. So I think this is a good problem in terms of starting with words and ending with like math, like numbers. So part A, or let's write down what we know first, or what we have. We have gross domestic product, which is G. We know that G is equal to $310 billion in 2007. So what we're going to say is I'm going to make this function G of T. And so G of 0 equals 310, where T is years after 2007. So that's where I'm going to start setting up this equation. So now I have an independent variable, which is time, and I have a dependent variable, which is my gross domestic product, which is dependent on time. Now we get to look at how this G changes. So for part A, we have a 3%. So G is increasing by 3% per year. How do I interpret this into a equation? What kind of equation is this going to look like? Well, I have a percentage, and I know it's a growth. So I'm going to say that my growth rate is equal to 3%. And we have a function that we know looks like this. That's going to be g of t is equal to my initial value times, and we're going to make this growth, so it's going to be 1.03 to the t. So this is my there. So it's going to be 1 plus 0.03, and that's going to be to the t. So as t increases, g of t increases. So that makes sense with what we're given in terms of figuring out what this problem is. And so this is going to be, t. It's going to be my answer. All right. Now you guys help me out, not with B, with B. So now we have $8 billion per year. What is this function going to look like? Thoughts, comments, concerns? Is this going to be an exponential function? Let's start with that. Are we going to be able to put this into exponential form? No, exactly. This is not going to be exponential. Something that my biggest tip for you guys when it comes to math is if something doesn't seem like it's going to work, it's probably just not going to work, because this is a lot of just like logic stuff. So if I were to try to turn this into some sort of an exponential function, it just wouldn't work very well. So what I'm going to do instead is I'm going to make it a linear function, because that's what makes sense. So g of t is going to be equal to $8 billion per year plus my initial value. So here's my initial, and that's going to be plus 8 per year. So if I were to say, let's look at 2010, that would be t equals 3. So g of 3 is equal to 8 times 3, or 24, plus 3, 10. So it's just going to steadily increase at a rate of 8 per year. And so that is my linear one. And this is going to be my exponential one. So you can see in the long term, you want exponential growth. But if you're talking about like something like money. So that is the difference between these. Everybody okay with what's going on here? Yeah, basically, it's important to be able to use exponential functions, but also recognize when not to use exponential functions. Do you guys want to do more questions in terms of exponentials? Do you guys feel relatively comfortable with analyzing exponential functions? Yes, for sure. I can do one more. Okay. So, if you guys have any suggestions for which problem you want to do, I'm just looking over some problems right now. We can try maybe 20. Oh, number 9. Sounds good. Okay. And so we're on page 43 still. Okay. So an air freshener starts with 30 grams and evaporates. In each of the following cases, write a formula for the quantity Q grams of the air freshener remaining T days after the start, and then sketch a graph for the function. So this is essentially the same sort of thing that we just did, but in terms of decay. So we're going to go over what we have and try to design what this function is going to look like. So we have Q, which is a function that is dependent on T, right? And so this is going to be the number of grams over T time since start. So essentially, we start the air freshener and it's going to evaporate. We know that Q of 0 is equal to 30 because that's how much we have at the start, so 30 grams. And now we are trying to generate a formula that shows a change of 2 grams a day and a change of 12% a day. So let's start with 2 grams a day. Is this going to be exponential or not? Yes, it's going to be linear. And it's going to be Q of T is equal to 30 minus 2T, exactly. Because this is our initial value and this is our change over time. So it's going to be exactly that. And so for B, it's going to be 12% a day. And so this is going to be exponential. But we have to make sure that it's a decay function. So our Q of T is going to be equal to our initial value times, and so is this going to be 1 point, when is it, a percent? Yeah, I would essentially say that, like, if you're trying to design an equation and it's saying it's changing by percentage, go with an exponential equation as a good, like, I hesitate to say that this is the case every time, but I'm pretty sure it's the case every time. So are we going to be greater than 1 or less than 1? Going to be less than 1, exactly, and it's going to be 0.88. And this isn't 0.88%, it's going to be 12%, so it's 1 minus 0.12. Yeah, exactly. That's fine. I just want to make sure that everything's on the right page. Okay, so now we have these 2 equations. And yeah. Now we're going to kind of sketch a graph. And so this is going to be 30. Come on. And this is going to be time. So this is going to be 30 minus 2t, so this is going to be a line, and it's going to intersect with this here. And it's going to intersect with 0 at what, 15 days. So this is t equals 15, right? Yeah. So we're just sketching this graph. T is in days, right? Yep, T is in days. Okay, so Q is equal to 0 at 15 days. And that's what this intersection means. What about this? So here, it's going to go down pretty fast, and then it's going to go like this. So we're going to start at 30, just like this linear function did. But one of the characteristics of an exponential function is that it gets close, but never reaches 0. So that's sometimes a concept that is like a little bit difficult to understand, but basically, no matter how tiny this t gets, this is always going to be like a number, and it's going to get very, 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 very close to 0, but it's not going to technically be 0. You can round it to 0, but it's not actually 0. It's just very, very, very small. Is everybody okay with that? So in terms of sketching this graph, the only one with the actual intersection with the x-axis or the t-axis is going to be the linear equation. Infinite air freshener, exactly. Well, and I mean, like, if we're looking at this, it makes sense because we're like 12% per day. So if I have like 30 grams, like, and I get rid of 12% of that, and then I get like however many grams after that, and then 12%, and then I have just like a very tiny amount, but 12% of a very tiny amount is a very tiny amount. So infinite air freshener. Somebody better to design one of those. Okay. Any more questions? Yeah, I can definitely do number 20. Okay. Okay, so we are, we're given this function, p is equal to p naught a to the t, and we are finding values for a and p naught, and we are stating the initial quantity and the percent rate of growth or decay. So, p naught a cubed equals 75, and p naught a squared equals 50. Okay. So, what are we going to do? How are we going to start this? We actually, if we were to do that, we wouldn't have an answer because we're not given an initial value. So we're only given this information about when t is equal to 3 and t is equal to 2. We don't know what's going on with t equals 0 right now. So my gut instinct when I see two equations that have the same term, p naught, is to set both of them equal to p naught. So here it would be p naught is equal to 75 divided by a cubed, and here it's p naught is equal to 50 divided by a squared. And so I know these are both the same p naught, so I'm just going to say 75 over a cubed is equal to 50 over a squared. And so I'm going to multiply both sides by a cubed and a squared. So I can end up with an equation that I can work with. And so that is going to be a squared 75 is equal to a cubed 50. Now I have a bunch of this a floating around. So I'm going to divide both sides by a squared. And in terms of exponents, so this is going to cancel. And you can think about it in terms of a 3 minus 2, or times 50 is equal to 75. Or if you want to think about this in terms of a times 50 divided by a times a. So you get rid of 2 a's here, 2 a's on top, and we end up with a times 50 is equal to 75. So divide both sides by 50. So a is going to equal 75 divided by 50 is 3 over 2, right? 3 over 2, yeah. So I'm going to erase this and set this up again. So a is equal to 3 over 2. And we know that p naught a cubed equals 75. And p naught a squared equals 50. Okay, so basically the whole point of this problem is to take information that we have floating around and turn it into like actionable information. So now we know what a is. We can say that we can put a into one of these equations. We can say that p naught times 3 over 2 squared is equal to 50. And then we can say that this is p naught times 9 over 4. Because of the way that exponents work, we can put the squared here and just divide them like that, equals 50. So I'm going to multiply both sides by 4. So this is p naught times 9 is equal to 200. And then I'm going to divide both sides by 9. So p naught is going to equal 200 divided by 9. And you could put this in to like actually get a decimal, but yeah. So part A is we're asked to find these parameters. So there is our p naught, and here is our a. So now we are asked to state the initial quantity and the percent rate of growth or decay. So our initial quantity is always going to be p naught. So this is our initial. And our A is going to tell us, is this growth or decay? So this is larger than 1. So it's growth. And our rate, we can write this as a decimal point. So it's going to be 1.5. So our rate is going to be 50%. And that is question 20. So we do some algebra to find out what A is, and then we use A to find P naught, and then we use that information to determine initial value, and we can use A to determine growth rate. So the point of this question was just kind of to like be able to work with some exponential functions. And this basically sets us up. This is our t equals 0 position. So now we're prepared to do some work with this equation. Any more questions? Guess I'll take that as a no. Okay. I think that will wrap us up for today. But if anyone has any more questions about this material, or especially next week, I was reading the comments about what dates would be best, and we'll figure that out for next week, just to make sure that we have a steady, excuse me, a steady meeting time. And if anyone has any questions about this material, send it to me during the week, and we'll get set up and talk about it next time. All right. Thank you guys for coming. Thank you for sticking around. You guys have a great day.